All right, let's get started on integration by parts. So in this lecture, we're going to be looking at a different method of doing integrals than substitution. So we've seen integrals where we've just had simple ones where you just answered it, basically just with the power rule or an exponential rule or a logarithmic rule or something like that. And those are pretty simple. There was nothing really tricky involved. You were just using a formula that or a rule that we had developed. And then we talked about substitution, which was this tricky way of rewriting an integral in another way. So when we did a substitution, we actually said, hey, let's let u equal something in terms of x. And we actually turned the integral in something in terms of x into something in terms of u. But really, that's just a way to rewrite that integral. And we obviously had different notation where we changed from x to u, but it doesn't matter what letter you use. You could change it from x to x as long as you did the appropriate substitution. Well, here what we're going to do is we're going to come up with another way to rewrite an integral so that it becomes easier to do. And just to start off here, I actually want to go ahead and look at the product rule. What we're going to see is very closely tied to it. So I'm going to be careful with my notation here. I'm going to use this ddx notation, and I'm going to be explicit at first and write that consider I have a function that looks like u times v. And I'm going to make sure that those are functions of x. And so we've seen the product rule before for derivatives. This should be just recall here. We've got u prime v plus v, or excuse me, u prime v plus u v prime. So if we take this, first thing that I'm going to do, I'm going to get rid of all these of x's. I just think it looks a little bit ugly. We know that u and v are functions of x. Let's just go ahead and simplify this down a little bit and just write u prime v plus u v prime. Great. So we've got this. I'm going to rearrange this a little bit. I'm going to solve for this guy right here. So if we solve for that, I'm going to have u v prime. Basically what happens is I take this derivative and I leave it right as it is. And then I subtract over the u prime v, just subtract over that term right there. And so we've got that right there. And now I'm going to do something that we've never really talked about doing, but it should make sense. I'm going to take an integral of the entire equation. And you could think of this like we've done before, where we've taken a derivative of an entire equation. We've done that on graphing for finding relative maxes or min. You would take a derivative of your equation and set it equal to 0. And so, or even an implicit differentiation, we did that, where we took a derivative of the whole thing. So here, I'm going to take an antiderivative of the whole thing. And what's going to happen most of the time here is basically we're just going to end up with a bunch of integration signs. And remember, u and v are functions of x, so I'm going to make sure to write a dx there. And now here's the catchy part, though. I have a derivative of a function uv. If I take an integral of the derivative of something, basically that integral and derivative just cancel out. And so I'm just left with uv and then integral of u prime v dx. So we've got this right here. This actually is integration by parts. Generally, what we do, though, is we take the v dx, or excuse me, we take the u prime and the dx, and over here, we take the v prime and the dx, and we kind of just lump them into one whole thing. We just call this whole thing dv, and we call this whole thing du, just what's in the orange. The reason that we're doing that, it's probably easy to see with this v prime dx. What happens here, if we started off, I'm going to get rid of that for a second. If we started off with v is a function of x, so it's something, yada, yada, yada. what's going to happen is I'm going to take a derivative, and I get dv is whatever the derivative of v is, dx. This is exactly what we've done with u substitution. Right here, I'm just using the letter v here. So got that right there. I've got this right here. If I were to do u is equal to u of x, right? It's a function. If I were to do just exactly what we always do with u sub, we've got that right there. And so what we're seeing here is just for shorthand, instead of writing v prime dx and instead of writing u prime dx, I'm just going to say, hey, that's dv and du. It's just like what we've done with u substitution here, where we start off with u equals, I don't know, x squared, and then you say du is 2x dx. Well, that 2x is just the derivative of whatever the function was, in that case, x squared. So we've got dv and du. Let's get rid of these arrows over here, clean this up a little bit. So we've got all that. And the last step that we're going to have here, I'm going to put it in red. It's the same thing, but it's just u dv equals uv minus integral of, there's the v, and then du. And this is what you're going to hear when we talk about integration by parts. What we're saying here, just to explain this a little bit more carefully, we're saying that if I have an integral that looks like this, meaning there is a function of x, remember u is a function of x, we saw that up here. So if I have something like this, and there's a dv, which remember is really just a dx times a v prime. So if I have an integral that looks like this, then I can rewrite it this way. And what we hope is that when we rewrite it this way, it's easier to do. So the trick here is going to be to try and be able to look at an integral and ask ourselves, all right, does it look like this? Can I write my integral in this format here? And we're going to get some practice with that. So this is integration by parts, and did all that work right here. Skip over that. We just did that. So we've got this integral of u dv equals uv minus integral of v du. So this is a way to rewrite any integral that looks like this into this format. And so what we have to do is we have to look at our original integral. The thing that I'm asking you to take a derivative of, you have to identify u and you have to identify dv. You're going to notice that in a lot of these examples that we'll do, you're going to have two pretty distinct parts to the integral. One of them is going to be u and one of them is going to be dv. Well, once we have u and dv, we can very easily find du by taking a derivative of u, and we can very easily find v by taking an integral of dv. And then once we're done, once we have all that, once we have all four of these, you'll notice I have a u, a v, another v, and a du. So I just plug those three things, just u, v, and du, into this side of the formula, and now we've rewritten our integral and we're on our way. So let's go ahead and do an example here. This is an integral x e to the x, and try as you might, you can't use substitution and you can't use any of the simple formulas, the simple rules that we've come up with before. They don't work. Substitution, as much as you might try, there's really nothing you can do. What I do notice, however, is that this integral has two pretty distinct elements to it. It has an x and it has an e to the x dx. Or really what we could say is it has an x and an e to the x, because the dx is just always going to be there. So I see these two distinct parts, and that's actually an indicator, that's a hint that integration by parts might work. So what I'm going to do here is I'm going to say, let's try integration by parts. And remember, the first step here is we need to identify the two parts of our original integral. And we've done that. We pointed that out, x and e to the x here. So the question is, which one of them is u and which one of them is dv? Well, I'm just going to go ahead and start off and choose the appropriate choice, and we'll talk about how to choose that, how I know that that's the appropriate choice. We'll talk about that after. But for now, what we're going to say here is that u is going to be equal to x let's go ahead and make that big. U is equal to x. And then dv, I'm going to set equal to e to the x dx. And remember, what we saw way back here was that this dv that we're writing is just shorthand for v prime dx. It's just shorthand for some derivative dx. And really, when I say some derivative, that's just a function. It's just something. In our case, in this example, it's e to the x. It's just something in terms of x, dx. And so you notice that here, this dv, I'm writing it as something dx. And so what we can do here is we can work forwards. Let's go ahead and change the color here, let that match the orange. We can work forwards on our u by saying, hey, if u is equal to x, then du is just dx, right? If you take a derivative of x, you just get 1. Don't forget your leftover chain rule dx. Now we're going to work backwards here on dv. We have to take an integral. And so the integral of e to the x dx is just e to the x. We won't worry about a plus c here, not really necessary. It's, yeah, not really necessary. It will end up having a plus c later in the problem, so we don't need it right here. But at this point here, I've got my 4 things. I've got u, v, du, and dv, and we're happy because at this point, we're able to move forward with integration by parts. I've identified my u and my dv, and then I've worked forwards and backwards with derivatives and integrals to find the other corresponding du and v. So what we can do is we can use the integration by parts formula to rewrite this integral. And let's go ahead and do that. So we're going to have the integral of x e to the x dx. And remember, our formula, let's go ahead and write this. Our formula is the integral of u dv is equal to uv minus the integral of v du. So we've got that right there. And let's match this up. So here, we'll copy this over here. So we've got our u, v, du, and dv right there. So if we just copy this in, we have u is equal to x, v is equal to e to the x, minus the integral of v is e to the x, and du is just dx. And at this point, I stop and I take a note. I ask myself, is this integral right there simpler than the integral that I just did? Most of the time, it will be. If you've done things correctly, it'll be simpler. The goal is to make this simpler. And what I will say is it doesn't always work out that way. In a very few problems and in a couple very specific cases, sometimes this gets more complicated and then it's still possible to do the integral to finish it all out. But most of the time, if this is simpler than the original integral, you've done it. You've done a good job there, and you've set the appropriate u and dv. You've chosen these guys appropriately, the u and the dv right there. So what you might notice if you practice this on your own, I would actually recommend doing this. Try changing the u and the dv. So instead of setting u equal to x and setting dv equal to e to the x dx, flip those and then see what happens. You'll notice that this doesn't get any simpler. It actually gets more complicated, and that's bad. But we'll talk about how I knew to set u and dv to what they were in just a second. So we've got this integral. This is just an equivalent statement. I've taken an integral and I've just used this, basically the product rule. Remember, we started with the product rule and we rewrote it into this formula that I'm calling integration by parts. We're using integration by parts to rewrite this. So this is fully okay. This is good. And at this point here, I just have a nice, easy, simple integral. Integral of e to the x is e to the x. Don't forget your plus c. You may be picky and you may want to do that. That's okay. When you distribute the minus sign into that constant plus c, it's just going to give you a new constant, which I'm just going to call c. So a lot of times we just kind of tack on that plus c at the end. And then here I'll do a little bit of factoring. I'll factor out an e to the x because that makes it look really nice. And there we go. We've got our answer. We've done this integral right there. And what we've done to do this integral is we've written it in terms of a function and a simpler integral. And that's exactly what integration by parts does. So let's continue on here. What I want to do is I want to do the same integral, but I want to add some limits to it, some limits of integration. So in this case, I have limits of integration from 0 to 2. And we use the same formula for integration by parts because we see that integrand, we recognize, hey, integration by parts, and we just did all that work. We know what we need to set to u and dv, and we know what we can do. Well, when we have these limits of integration, what happens are two things. One of them is fairly obvious. The integral that we have left over, we got to keep the a and the b there. We got to keep that as as what they were originally. But the other thing that some people forget is you have to evaluate the first term at a and b. You have to evaluate them at the limits of integration. If you don't, you're going to end up with an x in your answer, and that's not good if we have a definite integral. Remember, this definite integral needs to be a single number. It needs to be a value, a numerical value, because it represents a Riemann sum, which talks about area. So don't forget this evaluation at b and a, and then obviously the limits from a to b there. So if we do this, I've got this work written right here. What you'll notice here is that ignoring all of these limits here, this looks exactly like it did before. I'm just copying the work that we did previously. When we did the integration by parts on this step right here, I had the x e to the x minus integral of e to the x dx. And let's actually do this. Let's go ahead and write that. I can kind of highlight that. This what's highlighted in the red is what I had previously. The extra stuff, we could highlight it in blue if we wanted to. And that extra stuff is exactly just those limits that we had before. So we've got that right there. Now, obviously, when I do this integral, it's just still going to be e to the x evaluated at 2 and 0. You'll notice here, because my evaluations are the same, I can combine these like I did before. You don't always want to do that if these are different, but the good thing is that with integration by parts, they always will be the same because they have to, because they came from these starting limits. So I combine everything, and then at this point here, it's just a normal definite integral. At that point, I'm just evaluating this function at 2 and 0, and I end up with a nice e squared plus 1. So on a definite integral, we have a slight difference here. We still use the same formula. We use the same result, as you can see in the red all here. But we obviously have to evaluate and add in what we've got in the blue right there. Now, I've talked about it long enough. I've said it a handful of times. How do we pick u and dv? Well, what we want to do is we want to pick u and dv so that u gets simpler when you take a derivative of it, and dv gets simpler when you integrate it. And the reason for this should be fairly straightforward. We're starting off, I like to make this table here. We're starting off with u and dv, and we get to choose what we want them to be. And this u, I'm going to end up taking this, and I'm going to take a derivative to get du. And then for dv, I'm going to take an integral to end up getting v. And so what we would hope is that when I do these calculus derivative and integrals, when I do these calculus things, right? These expressions, these derivatives, these integrals, then we want things to get simpler. So if I pick u and dv such that they get simpler when I take a derivative and then simpler when I integrate it, respectively. That's good. That's helping us make things simpler. If they get more complicated when you take a derivative of them, that's not necessarily a good thing, or a derivative or integral. You don't want things to get more complicated. So that's generally a good rule of thumb. The second good rule of thumb, as I mentioned before, is that we want that resulting integral to be simpler than the original one. And we saw that back here. We had this integral right here was simpler than the original integral. And that's good. That's what we're generally going for. As I've said, it's not always the case. Sometimes there's exceptions. But this is a pretty good, these are both pretty good rules of thumb to follow. So let's go ahead and do another example here. So we're going to integrate from 1 to e of ln x divided by x squared dx. Now, we look at this here and we know, because this is a lecture on integration by parts, we can it's pretty easy to assume, hey, we're going to do integration by parts. But if you saw this just with no context, you might try to do a u substitution first. And if you tried to do a u sub, you might say something like u is ln of x. You might try something like u is x squared. Maybe there's different choices that you would try, but what you're going to notice is that the more, or all of these that you try, they're not going to work. So if none of that substitution works, a possible route to check is integration by parts. There are other routes you could check. You could try just using one of your rules if substitution didn't work. You could try simplifying the integral in some way. But in this case, integration by parts is going to be the way to go. So let's do our integration by parts here. I'm going to go ahead and write u equals, I'm going to write dv equals. And note here that I don't exactly know which is which. I don't know which would be smart to set to each. And to me, it seems like there's kind of two options here. I mean, I'm going to go ahead and write out both of them. So one option, it seems to me like my parts of this are ln of x and x squared. So maybe I could flip it and I could say, hey, do this. Let's just try both of them. If I set u equal to ln of x, then du by taking a derivative is going to be 1 over x dx. And then v by taking an integral is going to be 2x. Oh, and careful, dx, can't forget that right in there. dx, can't forget those. So we've got that right there. And let's go ahead and do this bottom guy. du is equal to 2x dx. V is equal to the integral of ln of x. That's tough. We haven't actually seen that very explicitly. If this integral right here isn't simple enough to do really in our heads, or maybe with a quick work off to the side, we probably haven't chosen the right things. And so this whole method right down here, this whole idea of u equals x squared and dv is ln x, just doesn't quite work. And so this is exactly what I'm getting at, where just try things. And if it's not possible really to do it, I would maybe say, hey, try to do the integral of ln of x. What you'll notice is that it's hard to do. It's tough to do. And so we can't even get a v up here. So this method down here, we probably just shouldn't do it. So we've got this. This is good up here. We've got all this here. The question is, we want to check this though, because remember, with integration by parts, what we're trying to do is we're trying to rewrite this integral in terms of u and dv. We're trying to make this integral here look like integral of u dv. And I noticed something here. I noticed that I set u equal to ln of x. So let's come off to the side here. Let's say, hey, u and dv, right? We hope that our integral in the blue looks like this in the green. Well, based on what I've written here, u is ln of x, and dv is x squared dx. I'll go ahead and put some parentheses here just to make that look a little bit cleaner. Here's the question though, does the green match the blue? Obviously it doesn't. And this is a very common mistake that I've made purposefully here to hopefully point it out so that you don't do it. It's very easy to look at ln of x and to look at an x squared and just say, oh, cool, my two parts are ln of x and my other part is x squared. So I just set those right in there. But the problem is that if the whole goal is to get this to look like that. And based on our writings in the red here, this integral looks like this, not what I have. And so this setup here, it doesn't even work. This is also wrong. So we got to be more careful here. And how we need to be more careful is we need to do dv is 1 over x squared dx. Again, for the same reason, we wouldn't try to have ln of x be dv, and we wouldn't try to have 1 over x squared be u, because that's just, it doesn't work. We don't know how to simply take the integral of ln of x. But here, 1 over x squared, that's pretty straightforward to take an integral of. We've got 1 over x squared. If we were to rewrite this as x to the -2, if we were to take an integral of this, we would add 1 and then divide by that resulting power, which, simplifying this, we'd have -1 over x. So just power rule right there for integration. And we're seeing that we actually get a -1 over x right there. And at this point, we've actually done this grid, we've done this table correctly. You'll notice that if I look at my u and my dv, and I write them out explicitly, my u is ln of x, and my dv is 1 over x squared dx, and this matches that integral right there. So we're good. So we've chosen the right u and dv. Just as I've gone through slowly, you got to be careful about how you choose your u and dv. They have to match up so that it's in here. Don't just look at ln of x and x squared and just think, ooh, one part, second part, one part, second part. You have to make sure that your u and dv formulate together to give you that integral in the blue. So we've got this. Enough chit chat. Let's go ahead and rewrite this guy. So we have uv minus the integral of v du. Bunch of parentheses here just to make sure that we keep things nice and clean. And I'm forgetting here, we've got our limits. Don't forget the limits on this other guy. At this point, everything's pretty straightforward. We're just simplifying and doing a simple integral here. If we end up with, give me a second here. Let's make sure this all looks good. Cool. So we've got this here. If we were to say negative ln x over x, just simplifying that, again, still evaluated at 1 and e. I haven't done that evaluation yet. This integral, I'm not going to take the integral just yet. I'm going to simplify here. What I notice is that I have a minus sign and a minus sign. So that's going to yield a plus sign out front. And then I have a 1 over x squared right there. So we've got a 1 over x squared dx. And yet again, 1 over x squared is a pretty simple power rule integral. In fact, we've already done it right here. So maybe keep that work that you've used, because you might be able to reuse it like we get to here. So if I have negative ln x over x evaluated at e and 1 still, not going to bother, I'm just holding off on that evaluation. If I do this integral, as we already did, I have minus 1 over x. We saw that right there. So I still have to evaluate this at 1 and e. I'm going to do that little trick where I combine all of this. Negative ln x plus 1 over x, evaluated at e and 1. And what you'll notice what I've done here, so a little careful, there's a negative sign here that I've brought out front. I've brought this minus sign out front, and I've looked at the common denominator of x right here, and I've made it all one denominator. And so because I've factored out this minus sign, I actually have a plus here. Be very careful in the way that this is written. If I move this minus sign, if I accidentally put that up here, then that looks like negative ln x plus 1. If I put it down here, that looks like a minus x. I want to be very careful. I want to make sure that I'm being clear that the negative is out front of that fraction. What you could even do is you could even put it out here. This would be perfectly acceptable. For now, I'm actually going to go ahead and leave it like that. I'm going to leave that minus sign out there. So we've got this. At this point, just nice and simple algebra. We're just going to plug in e and plug in 1, and we'll be on our merry way. Let's go ahead and do that on a new slide. So just continuing this work here, we have negative ln e plus 1 over e minus yet another negative. So here, let's do this. In the brackets, that's my evaluation at e, and then in these brackets, my evaluation at 1. A lot of negative signs, so you got to be careful. So we've got all that plugged in. I just plugged in an e and a 1 in for x, and I subtracted them. And just simplifying this all the way down, ln of e is just 1. So we've got negative 2 over e. Minus and a minus are going to cancel. I'm going to have plus. Ln of 1 is 0. 1 over 1 is just 1. So at this point, we're basically just done. I'll just simplify this. 1 minus 2 over e. And there we go. We've got our answer right there. Great. So let's wrap this up. Let's look at 2 more quick examples. We're not going to do the integrals, but we're just going to practice choosing our u and our dv. Split this down the middle here. So we've got the integral of x squared e to the x, very similar to actually what we've seen before. And we've got a 2x plus 1 over e to the x. Again, if you saw these out of context, you'd probably start by trying to do a u sub or use just a rule. But after some guessing and checking and some trying, nothing's going to work, and you're going to have to do integration by parts. So if we set a u and we set a dv, we're going to set a u and we're going to set a dv. We're going to try, we're going to hope that things work out. And keep in mind those rules of thumb that we saw. Generally, we want u and dv to be simpler when we take a derivative and an integral respectively. So if I were to set u on this first example, if I were to set u equal to e to the x and dv equal to x squared dx, the rest of it, the problem with this is that when I integrate x squared, I get 1/3 x cubed. And to me, I've made that more complicated. I've turned this into from a quadratic into a cubic. I've actually added a power of x by integrating here. That's not good. Here, it's not any simpler than it was before. So this choice was poor. We want to switch these. We want to actually do u is x squared and dv is e to the x, because now my du gets simple when I take a derivative. I went from a quadratic to a linear function, and that's good. And then here, when I integrate e to the x, I just stick with e to the x. It's no simpler, but it's also not more complicated. And because this guy gets simpler in that calculation, then this is good. We've made things overall simpler. We would go ahead and write this in the blue as equals to uv minus integral of v du. And actually, I'm going to be careful here. I'm going to write 2 x e to the x dx. This is my v, and then the 2x dx as my du is all of those that are underlined. And you'll notice I actually have an integral here that we've done already. This would require another application of integration by parts, but we know how to do that. We can just do integration by parts on this and plug it right in there and then just simplify. So there we go. Let's do this example on the right here. I'm going to go ahead and split this a little bit more clearly in white. There we go. So we have some options. We could try u equals to 2x plus 1. And then dv, remember, you got to be careful. Don't just look at that e to the x and say, oh, e to the x dx, yay, because that's not what it looks like. It's actually a 1 over e to the x dx. And now while this 1 over e to the x dx does look complicated, it's really just an e to the negative x. That's pretty easy to take an integral of. If we took an integral of that, we get negative e to the negative x. Here, my u, if I take a derivative of it, I just get 2 du. And this actually looks pretty good to me. This didn't get any more complicated than what it was before. I mean, sure, we added a minus sign from the integration, but it's still pretty simple, basically the same thing. And here we went from a linear function to a constant function. Ooh, that should be a dx right there. Just changed that. I had written du, but that's a dx. But here, we went from a linear function to a constant function, so that's a lot simpler. If I had made 2x plus 1 my dv and taken an integral of it, we would have ended up with x squared plus x, a quadratic function. We've gone from linear to quadratic in that scenario. That's not good. We don't want that. That's more complicated. So this is actually working out. We'll verify that it works out by writing this out. uv, there's u, there's v, minus integral of v du. Well, v has that negative sign, so I'm going to make that into a plus with those negatives canceling. And then we have v du. Well, I have 2e to the minus x dx. And when I look at this, that's a fairly simple integral to do. It's just an exponential here. In fact, if I pull out the 2, if I just pull that outside the integral right there, this integral here, we actually already did it. We did it right here to there. So there we go. We've actually done that already. And this is much simpler than the original integral. You'll notice this is much simpler than that because we actually already know this. We've done this integral with integration by parts. So it's very simple because we know the answer to it. And we've kept in mind that idea of letting u get simpler and letting dv get simpler in integration, or excuse me, in derivation and integration respectively. And same thing here. So we've got all that. That's integration by parts. Just as one last sort of send off here, just saying it out loud one more time. The integral of u dv is uv minus integral of v du. You'll hear that just with, sung kind of with a little jingle to it. uv minus integral of v du. Nice roll off the tongue right there. So that's integration by parts, just another method of solving integrals, kind of like how u substitution is a method for changing an integral. We've got integration by parts. It's basically just the product rule rewritten. So we'll go ahead and have that be the end of the lecture. That'll be integration by parts.